Good morning, my dear friends. I hope you all are doing great. So today I have come up with the problems on thermodynamics. So let us see the first question here. The mathematical expression or the mathematical form of first law of thermodynamics when heat Q is supplied to the system and W is work done by the system. So my dear friends, when we look at the first law of thermodynamics, I have already told you that the energy of the universe, that is system plus surroundings, will be always constant. So we derived an expression, if you remember, that was delta U is equal to Q plus W. This Q is basically positive here. This Q stands for heat absorbed by system. And plus W means work done on the system. So we derived this expression last time, if you remember, in first law of thermodynamics. Change in internal energy. This is change in internal energy. So the change in internal energy of a system is due to heat absorbed by the system and the work done by the system. But here, my dear friends, if you look at this question, you will see that heat Q is supplied. That means heat Q is actually supplied to the system. That means system is absorbing the heat. So heat will be positive only. That means plus Q. And W is work done by the system. So the work is done by the system. So work, when it is done by the system, it will be negative. But if you look here, this is the work done on the system. Correct? So let us write down the same expression like this now. Delta U is equal to, first of all, let us talk about when heat Q is supplied to the system. That means system is absorbing the heat. Okay? So it means we will have Q as positive. So Q is here, heat is absorbed by the system. Because we are supplying the heat to the system, so system will absorb the heat, correct? And W is the work done by the system. So work done by the system is taken as minus. So we won't have here plus W, we will have here minus W. So this minus W will stand for work done by the system. So we are supplying some heat to the system, so system will absorb the heat, so plus Q. And work is done by the system, so minus W. Okay, my dear friends. So this will be your expression for the first law of thermodynamics when heat Q is supplied to the system and work done by the system, okay, is basically W. So now, my dear friends, out of these expressions, if you see, the expression number second is our answer. What is the meaning of this? Heat absorbed by the system, work done on the system. What is the meaning of this? Heat absorbed by the system and work done by the system. What is the meaning of this? Heat lost by the system and the minus W is work done by the system. What is the meaning of this? Heat lost by the system and the plus W means work done on the system. So our answer is option B. I hope you have understood, my dear friends. Please make note of this. So dear friends, let's talk about the question number second. A volume of gas decreases from 500 to 300. That means this guy is our initial value and this is our final value. And you know that the value is basically decreasing from 500 to 300. So it is nothing but it's a work of compression. Work of compression means work is done on the system. And when the work is done on the system, my dear friends, work has to be positive. Correct, my dear friends? So let's calculate first of all Let's do the solution for this problem. Change in value is Vf minus Vi. So what is the final value here, my dear friends? That is 300 ml minus initial value is 500 ml. Correct? So the change will be here, my dear friends, that is minus 200 ml is the change. Let us convert it into liters. So it will be around 0.2 liters. So minus 0.2 liters. This minus will tell us that volume is decreasing. The meaning of minus here is that volume is decreasing. I hope you are understanding my difference. So after that, when a sample of gas is compressed, that means we know already that it's a work of compression only. What is the external pressure, my dear friends, with me? External pressure 0.6 atmosphere. So, because of this external pressure of 0.6 atmosphere, the gas is being compressed and there is a decrease in value. So, this negative sign stands for here, decrease in value. Decrease in value. Okay, my dear friends? So, we know the external pressure here, that is 0.6 atmosphere. Can we find out the work here? Yes, we know that work expression also. Work is equal to minus P external delta V. Yes, my dear friends? And that will be equal to P external is how much? 0.6 atmosphere. So minus 0.6 atmosphere. Let me write down 0.6 here. Then multiplied by change in value. Change in value is minus 0.2 liters. So it's minus 0.2 liters. Yes? Now my dear friends, it will come out to be 0.12. And we know that this is atmosphere and the change in value basically it's liters. So this is atmosphere liter, or you can say liter atmosphere we have here. So my dear friends, the work done is getting which value here? Positive value. I told you, work has to be positive because work is done on the system, so it has to be positive. So obviously we are getting a positive value here for the work. That means it's a work done on the system. Correct? Now afterwards, have a look here. My answers are basically in joules here, my dear friends. So let us convert this liter atmosphere into joules. And remember, 1 liter atmosphere is equal to 101.3 joules. Okay? So let us convert it into joules. And everybody knows now that work is equal to 0.12 liter atmosphere, as we have already done. So let's convert it into joules. It will be 0.12 into, in place of this now, we have to use joules. So we have to multiply with this 101.3 joules. And this will round off, it will come out to be around 12.156 joules. So the work done is basically 12.156 joules right out here, my dear friends. Now, in this process, during this process, 10 joule of heat is liberated. That means how much of heat is lost in this process, my dear friends? 10 joules of heat. 10 joules of heat is lost. We know that this is the work of compression, work done on the system because it's positive. So let us go further and simplify it, my dear friends. So we have worked or heat energy. In this process the heat is liberated, 10 joules of heat is liberated. So we'll write down amount of heat liberated. Amount of heat liberated. Liberated here means lost. How much of heat is lost? 10 joules. Yes? So when heat is lost, is it minus Q or plus Q, my dear friends? It will be minus Q. And we know that it will be yours minus Q because heat is lost. Correct? So now what we have to find out in this process, the change in internal energy. We have to find out this thing. So what is the change in internal energy? This is our change in internal energy. And as far as the first law of thermodynamics is concerned, my dear friends, we know that delta U is equal to Q plus W. That is the expression from the first law. But here also we know that this Q is basically the amount of heat liberated or lost. That is 10 joules. So this heat is basically lost here. So is it plus Q or minus Q here then? It will be minus Q. And work is done by the system, so it is positive. So work is positive only. So in place of this now, minus Q, I will write down 10 joules. And that 10 joules will be minus only. So we have 10 joules here. And how much of work is done by the system? It is 12.156 joules. Correct, my dear friends? So how much will be the change in internal energy? So 12 minus 10, it will come out to be 2.156 joules. So that is the change in internal energy. Why did I write down minus Q here, my dear friends? Because we know that amount of heat liberated or lost is equal to 10 joules. And that 10 joules represents minus Q. That means heat is lost actually. So we have here minus 10 joules. That represents heat is lost. And plus W represents the work is done by the system. And we already know how much of work is done by the system, which is positive, 12.156. So finally I got 2.156. So obviously this, if we do round off of this, it will be approximately equal to 2.16 joules. So obviously 2.16 joules is the answer. I hope everybody has understood this thing. Please make note of this. So dear friends, let's go for the question number 3. A gas expands from 0.1 liter to 0.25 liters at 300 Kelvin temperature against a constant pressure of 2 bar. The work done by the gas is. You know that a gas expands, that means it's a work of expansion. When it's a work of expansion, that means work is done by the system. When work is done by the system, work has to be taken as negative. That means your answer will be the B option, my dear friends. So let us simplify it. Let's give the solution here, my dear friends. First of all, we know this is the initial value and this is the final value. So what will be the change in value? Vf minus Vi. How much is Vf? 0.25 liters. Initial value is what? 0.1 liters. So it will come out to be 0.15 liters. And afterwards we have the P external. External pressure is constant, which is 2 bars. So 2 bar is the external pressure. So what will be the work done, my dear friends? That is minus P external delta V. So minus P external basically is how much? 2 bars into delta V. Delta V we got it as 0.15 liter. So it will come out to be 0.30. You know that pressure is bar and the value is in liters. So I'll get liter bar. And it is given here, my dear friends, in the question itself that 1 liter bar is equal to 100 joules, because my answer should be in joules, my dear friends. So what I am going to do here, I will multiply this liter bar with 100 joules. So it will turn out to be 30 joules, my dear friends. But we know that minus sign is here. So keep on following the minus sign here. Minus sign and minus sign. So we have here 30 joules, man. So this is our answer. Please make note of this. So dear friends, let's go for the question number 4. When an ideal gas is compressed adiabatically. Adiabatically basically here means, okay, walls of the system should be adiabatic, which means no heat exchange between system and surroundings. So there will be no exchange of heat between system and surroundings. And when they tell that the work is done reversibly, that means you can use this expression also. This is not required, but whenever there is written reversible work, okay, then this expression can be used, my dear friends. W is equal to minus 2.303 nRT log Vf upon Vi. So let me write down it properly here. W is equal to minus 2.303 nRT log Vf upon Vi. So wherever there is written a term reversible, work or something like that, so this expression can be used depending on if value is changing. If pressure is changing, then this expression can be further modified, which I will teach you in next class actually. It can be also written as minus 2.303 nRT then log P initial upon P final, because pressure and value has inverse relationship, so I am inverting the terms here. So what is the question? This is a very simple question, my dear friends. If an ideal gas is compressed adiabatically and reversibly, okay, the final temperature is, what will be the final temperature of the system? Okay, this is just an information for you people. So it's very simple thing. If we have an adiabatic system with us, let's suppose this is a adiabatic wall, and the work is basically, its gas is compressed, that means work is done on the system here. Work is done on the system. Correct? So now this work is basically which work, my dear friend? This is a reversible work. Okay? So when it is basically compressed, what will happen? The internal energy, remember always thing, work is done on the system. So because of this, delta U, that is internal energy, change in internal energy, or we can say that internal energy of the system will increase. We write down internal energy of system increases. Another thing, when internal energy of the system increases, it means temperature of system will also increase. So temperature of the system will also increase. But remember, this wall has to be adiabatic wall. Why it has to be the adiabatic wall, man? Here we have ideal gas here. Because when you are doing work on the ideal gas, on the system, then the internal energy of the system will increase. The temperature of the system will also increase. And now, when the temperature increases, you can understand the heat content of the system will also increase. So heat will try to flow from system into surroundings. But you know that the wall is basically here, adiabatic wall. So heat cannot come out through this wall. No doubt we are doing actually work of compression. We are doing the work of compression. So here, my dear friends, P external will be greater than P internal. When you are doing work on the ideal gas, what happens? Internal energy of the system will increase. Temperature of system will also increase. Okay? Then, because of higher temperature in the system, the heat will try to flow from system into surroundings. But which is not possible. Why? Because the walls are basically adiabatic wall. And look here, walls of the system should be adiabatic. No heat exchange between system and surroundings. So the temperature of the system will increase. The heat will not flow from the system to surroundings. Work is done on the system, internal energy of the system will increase, correct? Temperature of the system will increase. Yes, I know. So initial temperature will be less and the final temperature will be more. So the point here is that higher than initial temperature. So final temperature is actually higher than initial temperature. Let me explain you once again. Work is done on the system. Internal energy of the system will increase. Temperature of the system will also increase. Correct? Then the heat from the system wants to flow out. But heat from the system cannot come out. Why? Because the walls are adiabatic. Heat cannot come out. Yes? So initial temperature of the system will be less and final temperature of the system will be more. So remember, the final temperature is higher than initial temperature. So that is my point actually, and that's your answer. Please make note of this. So dear friends, let's go for the question number 5. Which one among the following is not an intensive property? I told you that the property can be extensive or intensive. So this depends upon mass, okay, or size of a matter. An intensive property doesn't depend upon mass or size of a matter. So my dear friends, the pressure is independent of mass, my dear friends. So pressure is your basically the intensive property. So this is our intensive property. Okay. Density is equal to mass upon volume. This is mass is extensive property and volume is also extensive property. So the ratio of two extensive properties is an intensive property, my dear friends. So our density is an intensive property. Volume is basically an extensive property. It depends upon the mass of a substance. And temperature is again intensive property. I have already discussed these things, my dear friends. So out of these 4, the volume is the extensive property. Which one among the following is not an intensive property? The volume is the answer because it's an extensive property. It depends upon the mass. Please make note of this. Dear friends, let's talk about now question number 6. Which one among the following is an open system? So if you look at the thermos flask, I told you last time it's an isolated system. And in isolated system, everybody knows no exchange of heat or matter and matter, we can write down, between system and surroundings. Correct? And closed copper bottle, it's a closed system, my dear friends. And what is possible here? Only exchange of heat, no exchange of matter. Only exchange of heat between system and surroundings. Finally, we have pressure cooker. Is pressure cooker an open system or closed system, my dear friends? Pressure cooker is an open system. Yes. How come? Because if you are boiling water in the pressure cooker, so what happens? When the whistle blows, okay, what happens? The steam will come out of the pressure cooker. Okay. Steam, or we can say that on boiling water in pressure cooker, the steam is nothing but matter only, does come out, which means exchange of matter. And when we boil, actually, look here, when we boil the water, that means the heat is going from system into the, from surroundings into the system when we are boiling the water. Okay? When we boil water, heat, okay, moves from surroundings into the system. That means, this means actually exchange of energy. Exchange of energy. So here the first thing is that on boiling water, what happens? When the whistle blows, the steam comes out of the pressure cooker. That means matter is coming out. Means water is coming out, that means matter exchange is there. When you are boiling the water, you are supplying the heat from surroundings. Yes, and it enters into the system, and because of that heat, water is boiling. And even if you touch the pressure cooker also, you will feel the heat. That means heat is exchanged between system and surroundings. Correct? On boiling water, you are supplying heat from outside. Okay? When you touch the pressure cooker, heat comes out from pressure cooker into your hand. That means heat exchanges there. When the whistle blows in the pressure cooker, what happens? The steam comes out. That means metal is also coming out. That means both exchanges are happening there. So pressure cooker is an open system, my dear friends. So which one among the following is an open system? The answer is pressure cooker. Please remember that and make note of this. So dear friends, let's talk about question number 7. First law of thermodynamics for isothermal process, my dear friends. If we talk of isothermal process, my dear friends, here temperature of the process will be constant. Or we can say that the temperature throughout the process will be constant. When temperature is constant, it also means that delta T is equal to 0. That means change in temperature is equal to 0 because temperature is constant. We can also write it like this: T final minus T initial. And we know that T final is equal to T initial because temperature is constant. So delta T will be equal to 0 because both are equal. Yes or no, my dear friends? Now when the temperature of the system is constant, understand there will be no change in internal energy. Okay? So I will write down here now. When temperature of system is constant, then delta U stands for change in internal energy, okay, will be 0. That means internal energy of the system will not change. That means delta T is 0. That means delta U is also 0. That means change in internal energy will be 0. So if we write down now, after this if we write down the first law, mathematical expression of first law of thermodynamics, we have delta U is equal to Q plus W. We know that for isothermal process, delta U is equal to 0. So I will write down for isothermal process, change in internal energy is 0. So what is my equation? This equation will become like what? So it will become like this, my dear friends, now. In place of delta U, let's put this equation number 1. I will write down 0 because delta U for isothermal process is 0. So that's equal to Q plus W, and finally I will get Q is equal to minus W. That means work done by the system is equal to the heat absorbed by the system. Yes? So minus W means work done by the system is equal to heat absorbed by the system. Work done by the system. Because minus W means work is done by the system is equal to plus Q. So that means heat absorbed by system. Now you will ask me, sir, system is doing the work and heat is also absorbed. When heat is absorbed, temperature should change, but temperature is constant. There's a reason. Let us suppose if I am absorbing 1 kilojoule of heat, yes, and I am also doing, 1 kilojoule of work. That means whatever the amount of energy a system is absorbing in the form of heat, the equal amount of energy is used for doing the work. So total change is how much? 0. That means if I absorb 1 joule of heat and then I must do 1 joule of work, so temperature will remain the constant. Remember that particular point. So our answer will be the first option is our answer. Please remember that particular point. So dear friends, let's do the question number 8. Which one among the following is not a state function? We know that state function, it depends upon initial and final state of a system. And we know that internal energy, if we talk about the first one, the change in internal energy is equal to UF minus UI. So it's a state function. So it is a state function. And we also know that temperature, change in temperature is equal to T final minus T initial. So this is also a state function. Okay, if you look at pressure, the change in pressure is equal to Pf minus Pi. So this is also a state function, my dear friends. Finally, we have a work. Okay, it is a path function. You cannot write down work final minus work initial. So it depends upon the path of the system. Yes, if you cover up more distance, that means more work is being done. So that means the work is basically the path function, and even the heat is also the path function. So our answer is work. Which one among the following is not a state function? Internal energy is a state function, state function, state function. But work is a path function. It does not depend upon the final and initial state of the system. It depends upon the path, the distance, or the path of the process, the mechanism of the process, we can tell. Please have a look. Please make note of this. So dear friends, this was all for today. Catch you in the next class where we can discuss about the free expansion of the gas, about isothermal process, about reversible, irreversible expressions. I hope you have understood the today's topic. Have a great time. Thank you.